Hi, physics. What we're going to be talking about in this unit will be about measurements and errors and different types of calculations that we'll have to make with different units in this section. Anyway, have you ever looked at one graduated cylinder that we have in the lab here and looked at another and you've thought, well, gee, they look kind of different. How on earth did they make them so that each one is precise? How did they make sure that each one is accurate? Anyway, when I often wonder that, and then I realize, well, they have to make them according to different models that they go through, but there's errors with that. And those kind of errors we can't fix. Those are random errors. Another way of looking at random errors is to think about our lab, our STEPS lab that we were doing with the strides, I guess we should call it, and that your strides are not all the same. Each one that you walk may be the same, it may not be the same, and so we're trying to get an estimate of what the average is, and there's several places where your strides aren't the same, just like the graduated cylinders aren't the same, and just like the different meter sticks made from different companies, they're not the same. And those random errors we can't really do much about, but the systematic errors we can. The systematic errors are errors that are in our measuring. There are errors in using the wrong tools, so it's not done well enough. And also maybe even reading incorrectly. Remember those graduated cylinders, how hard it was to read that curved water line or that meniscus? And it was hard to read those, and so we would read them incorrectly. Also bad calculations. And if you had, inside that graduated cylinder, if you had some sand in there or some other volume in there that takes up some space, you're already off. And those errors are the ones that we can deal with. So those are the ones that we've got to try and eliminate to the best of our ability when we are doing our labs. Here was our strides lab, and this one's, I guess, is a depiction. It's drawn by Paul Hewitt again for active physics. Anyway, you notice that the two people there's a little girl and the big tall boy, and that they've got different sized strides. And so they're going to have different number of strides too for that length. And anyway, that's what type of errors are we talking about there? Those are some random errors that they're trying to show, but hopefully you can eliminate some of the systematic errors. Okay, this line seems like it's off a little bit, but this is going to be talking about accuracy, how close you are to that true bullseye. Okay, if you've got a result, like if you look at the periodic table and you've got a density it's got a density for aluminum as 2.70 grams per milliliter, and if yours is 2.69, you're really close to the bullseye. You're pretty accurate. The further out that you get, like if you get 3, you're not very accurate at all. Now precision, okay, this side is about precision. If precision is very different. It talks about the exactness of your measurement. Well, what does that mean? That means if you were talking about an instrument that measures like a graduated cylinder, like it measures 0.1 milliliters, or it measures, it's a big fat graduated cylinder, and each line represents 10 milliliters, then you're talking about this one is more precise than the one that's bigger, because it's got the calibrations are of much smaller units. Now precision is one other thing. If you also repeat your results over and over and over, very, very close to each other, you have a close cluster, that is also precision. So here's a question for you. What do you think about this? Okay, two students to measure the length of an object. One reports the length to be 3 meters and the other one reports the length to be 10 meters. Did one make a mistake? Well, I don't know what type of errors that there are there, but there is something. You know, it depends on what type of instrument that they were using. If they used the correct instrument, what was all involved in that? I can tell that they estimated the ones digit on those. We haven't talked much about significant figures, but we will soon. And anyway, there's some kind of error there. I'm assuming it's a systematic error. Now, on the next one, if a student reported the measurement to be 3 meters or 3.01 meters, did one make a mistake? That's showing the precision of their instrument. So there is no mistake there. That one just has that they used one that measured, that they had to estimate the meters. The other one they had to estimate the centimeters on that one. Okay, I believe you've got some spots to fill in on your notes on this one. These are the SI units. These are international system of units that are known internationally. Anyway, length goes in meters. Mass, you'd think would be grams, but it's actually kilograms. We base all the rest of our grams off of this one. Time is measured in seconds. This right here is chemistry, so you don't have to worry about that one. But a current is measured in amps or amperes, and temperature is not measured in Celsius, it is measured in Kelvin. And you'll notice that all of these are some type of metric system. I don't know quite if you call this one metric, but it is 273 degrees off of Celsius, and we'll talk more about that in the class. Candelas, those are candles. And like if you've got a spotlight, then you'll notice that they tell you how intense it is with however many candles of power it has. Mega, these prefixes, you've seen them before in physical science, and we go all the way from, we have to learn mega through micro. I'm going to give you a different slide. You notice that micro is the only one that's not by a regular, well, it's got a Greek symbol, mu, and it's got like a U with a tail on it. This one is the only one that has two abbreviations. I've also seen it with a capital D or a D, I think a DE, I'm not sure, but the DK is what I've seen the most. Mega is the only one that's capitalized, and it stands for a million. But here is what they all represent. I will zoom in on this portion. Here we go. And you can write down those values for it, for what each one represents. So we can also do some data analysis. We know that kilo represents 1,000, so that means that 1 meter represents 1,000th of a kilometer, or 1,000 meters represents 1 kilometer. Now, with those, I like using the whole number ones. I don't like using the decimals. So if you're going to do some converting, like this one here, I would convert with the bottom conversion factors that they've got here. Now I'd set it up in a ratio like we did in 7th and 8th grade math, and I would use the bottom one on this one. In fact, let's show you what I mean here. Here we're going to convert some units. We've got 10 kilometers. We want to convert that to meters. So you write with what you're given over 1. So we've got 10 kilometers, okay, and we're going to convert that into meters. So write what you're given over 1, okay, and then we knew that 1 kilometer equaled 1,000 meters. So you want to put kilometers on the bottom so you can cancel out those units. So there's 1 kilometer on the bottom, and then that equals 1,000 meters. So these cancel out. You're left with meters, which is what you're looking for. So that's great because you want that on the top of your fraction. And then we'll just get 10,000 meters. You'll note that in many European countries, they do not put the commas in those numbers. And if you're also from Germany, you'd put a period in place of commas. So it kind of is different how they write it out. Next one converts 3,600 centimeters. See, I didn't put the comma in that one. Anyways, 3,600 centimeters is what we're given, and we always put that over 1. And we're going to convert that into meters. So we want meters on top, and we want centimeters on the bottom. I know that 100 centimeters equals 1 meter. So I can go ahead and put that conversion factor inside this ratio, and I get 100 centimeters equals 1 meter. My centimeters cancel out. Okay, and look at this. I'll be dividing 3,600 by 100, so it's just going to be 36 meters for my answer. Okay, with metric it's pretty nice because you can also do some other conversions. You remember it goes kilo, hecto, deca, then the unit, like meters or whatever it is. In this case it'll be meters. Okay, then you've got deci, centi, and milli. Anyway, we're going from 0.72 kilometers. We're going from kilometers to centimeters, so it's larger units to smaller units, so we'll move our decimal to the right. How many places? We can determine that by going right over here and looking. Anyway, so kilo to centi is 1, 2, 3, 4, 5 steps down. So that means you move your decimal 5 places to the right. 1, 2, 3, 4, 5. So you're going to fill in those spots, and right there's your answer, 72,100 centimeters. Makes sense. Okay, now this time we've got 316 millimeters to kilometers, and now millimeters is going to be 6 spots, or 6 spots, going 6 spots up, and so you'll move your decimal place 6 spots. But since we're going from a smaller unit, millimeters, to kilometers, we'll move it to the left. 1, 2, 3, 4, 5, 6. So it's going to be 0.000316 kilometers. Okay, 2 students measure the length of an object and reports, oops, that should be reports the length of it to be 3 meters. I had a mistake in that slide, so I quickly found the right one. 2 students measure the length of an object